Hello, my name is Lauren Langmaid, and I've been working with Dr. Walker in Allene Synthesis. And specifically, we've been looking at studies in the hydridic reduction reactions of alkynyl hydrozones via sigmatropic rearrangement to form allenes. Allenes are important because they can be used as versatile building blocks in total synthesis, and this is due to their available center axis for chirality transfer. They can be used as electrophiles or nucleophiles. They're found in many natural products, and they're highly functional building blocks for synthesis. A lot of important work has already been done with allenes, and some notable synthesis for them can be seen here. So this top left figure, isolisirgol, it can be used as an antipsychotic agent. And the top right figure, isocyanometrine, that has high potent uterotonic activity, can actually be used for inducing labors. Taking a look at the retrosynthesis of this reaction, we will start with the methyl ester of lactic acid that can be converted into a variety of substituted inones. From there, we will convert the inone into a hydrazone, and then we will attempt a sigmatropic rearrangement to form the allene. So some good things about this synthesis are that it is inexpensive, and it's pretty straightforward and involves a lot of common reactions so that it's capable for undergraduate students to accomplish. And also the alpha hydroxy group that's formed could be further elaborated in some future synthesis. So looking in the forward direction of the synthesis, we started with the lactic acid derivative and added silver oxide as a Lewis acid catalyst. And to protect the hydroxyl group, we used benzyl bromide. Then, without purification, we concentrated the protected ester and added sodium hydroxide and ethanol, followed by an acid quench to form the acid. This process is also known as saponification. And once we had the acid, we formed the Weinreb amide using mesyl chloride and the Weinreb amide salt. So this is as far as we've gotten in the actual physical synthesis of the allenes. Everything from here on out is going to mostly be theoretical. But the next step in the reaction would be to form the inone. And we would do that by adding to the Weinreb amide a propionyl Grignard reagent. And there is an advantage in using the Weinreb amide for this, just because of the metal chelated intermediate phase and how that structure works to prevent over-addition of the Grignard reagent. So the next step will be the synthesis of E-alkynyl hydrozones, and we will achieve this by taking the inone and adding to it tosyl hydrazine to form this E-hydrazone. And we want the E-hydrazone specifically because that form is required to do a later reaction involving the formation of the allene using ADR. And we know that we will get the E-hydrazone from this reaction based off of a paper done by McIntosh. So he was using a similar reaction, and this lower left figure shows the results. As you can see, the E-hydrazone is highly favored over the Z-hydrazone. And the E-hydrazone is formed because of its potential for internal hydrogen bonding during one of the intermediate phases, and we can see this in the lower right figure. So taking a look at the possible mechanism for forming this hydrazone under microwave conditions, first the hydrazone would attack the carbonyl carbon on the inone, and then we would see a proton transfer where nitrogen loses a hydrogen and it is picked up by the oxygen, forming the intermediate phase. And then the nitrogen lone pair would kick out the hydroxide, which will then deprotonate to form the hydrazone. And we could take these results and verify them using NMR to make sure that we're getting this E-hydrazone as opposed to the Z-hydrazone. And this figure in the bottom here will show us that they both have different readings. So using NMR, if we see that 8 ppm, we will know that we have achieved the form of the hydrazone that we want. The last few steps of the synthesis involve the hydridic reduction of the alkynyl hydrazone via sigmatropic rearrangement to finally form the allene. And we will reduce the hydrazone to hydrazine by the reagent sodium cyanoborohydride. And we will use this reagent specifically because it is less reactive than some other reducing agents. And then the final step would be to heat the product and perform an allylic diazine rearrangement. So this is the portion where we really want that E hydrazone, as the rearrangement would not be possible with these Z hydrazone. And taking a look at this bottom reaction here, just to recover this portion of the synthesis, that first molecule we see is our inone, and added to it will be the tosyl hydrazine to form the E hydrazone, which then is reduced to the hydrazine, and then the last step will give us our allene. So this slide just covers some of the potential of allenes in future synthesis. So on the left here we have different hydrazones, and this is just to show that we could try this reaction on some more complex substrates. So the first one is a 4,2 cycloaddition, the second is a 2,2 photochemical cycloaddition, and the third would be the formation of a bicyclononane formed by a CH bond activation. All right, so that covers what I have been working on with this allene synthesis, and I would like to say thank you to Taylor and Micaiah, as well as Dr. Walker, for working with me on this project.